So what's going on, guys? If you remembered my last video that I made on the multiverse, or aka proof that the multiverse is proof that there's a heaven, this is how that ended up. This was my ending conclusion with all of that. My thought, and this is just a theory, it's just that, is that if there is a supernatural, spiritual realm that exists, I think it exists inside the dimension of time. So why am I talking about the second law of thermodynamics and entropy? Well, when we're talking about time being symmetric, it's noted that this law of entropy can happen the same way going forward in the future, and it can happen in reverse in the past. There's nothing about the law that says that entropy only happens in a forward motion of time. So what is causing our perception of time to only be able to perceive time as going forward? Interestingly enough, we have no idea, but there are some theories that physicists have come up with. So we're going to talk about those now. So one of those theories is that entropy, the expansion, the order into chaos, is what is causing the forward motion of time. But this is a problem because of what I just mentioned, that entropy is symmetrical to time. So it's our perception of it going in the future, going forward. But if we played it backward, it would also, the same laws would apply the same way. It would do the same thing backwards as it does forwards, going in the past as it does in the future. So there is a hypothesis that tries to dodge that bullet of symmetry, which is basically saying that it's called the past hypothesis, which was brought up by David Albert at Columbia University. And he theorizes that our universe began in a very, very low entropy state, and it's been expanding ever since. But here's the thing, we don't actually know if our universe began in a very low entropy state. The Big Bang, we don't know if it was a very low entropy. And Sean Carroll, in an interview that he did with the Royal Institution, said that he kind of relates that to the multiverse. Like, what if, and this goes along with the bubble multiverse theory that I talked about in the video that I did with the multiverse. And he says that an entropy, we don't know if there's another universe where the entropy just keeps growing and keeps going. So maybe in order, like the entropy in the other system, other universe, got so high that it just branched out into another universe, which is why our universe had such low entropy and it's been growing ever since. To me, that theory doesn't really make any sense, but that's just my opinion, and obviously this dude is a professional at what he does. So the reason that a lot of physicists don't like the past hypothesis is because it really just sweeps the problem of time under the rug. And it's just basically saying, well, the Big Bang did it, but that's kind of ignoring the point that time is symmetric, and these laws of the thermodynamics and entropy can apply the same way going forward as it can backward. So the past hypothesis is not at all by any means the final answer of what is causing the forward motion of time, but physicists kind of say that this is a placeholder for until we can figure out what actually causes the forward motion of time. So in 1970, British physicist Robert Penrose was actually the first to state the idea that entropy, the second law of thermodynamics, could be what's causing the forward motion of time. But by that logic, as we go back in time, we should be able to see more order in the universe, since, entropy is basically, like I've been saying, order and then it coming into chaos. That's what entropy is, the increased amount of disorder in a given system. So by that logic, if we go back in time, we should see more order in the universe. But we know as we go back in time more towards the Big Bang, that is not what we see. At the Big Bang, things were not in order, to say the least. So now comes in more philosophical questions. So if the Big Bang was the beginning of our universe and it did start in a very low entropy state, then we would be able to tell which direction the entropy is being expanded into, but we don't see that. So where did the entropy begin if it was that low? And where did the initial condition of entropy come from? Of course, there's that theory of the multiverse, but if that's not the case, then where did entropy come from? And obviously one possible answer is it was a stroke of luck, it was accident, but everyone's not okay with that answer. And also the problem of entropy is that it was actually evaluated in closed systems, which do not allow matter in and out of our universe. So it's not clear that these laws apply to the entire universe. It applies only to the closed systems that we have observed. One other theory that is what's causing the forward motion of time is a newer one, and that is gravity. Well, gravity isn't new, but the theory that it's causing the forward motion of time is a newer theory. So for experimenting if gravity is what causes the forward motion of time, they did this experiment where they built like a toy model of the universe, and basically it was filled with an array of like 1,000 different particles. And they observed to see how those particles reacted to gravity. So they found that the particles inevitably kind of clump together, and then once clumped together, they move back apart. And when they move apart, they stay in that state, and they never go back to the state of being clumped together. They just clump together and then they move back, and that's it. And really the law of physics, the theory in physics, I guess it's a law, that is at work here, at play here, is this thing called complexity theory. So this theory of the forward motion of time is gravity complexity theory. So basically, to explain this complexity and to better explain how gravity might cause the forward motion of time, imagine something that I'm sure all of you can imagine is a coffee cup filled with half milk, half coffee. I never add milk in my coffee. I always drink it black, but whatever. So if you drink coffee black, imagine that you have a coffee that is half coffee and half milk. Now, when you got the half milk at the top and half coffee, it's a very simple structure. You got milk molecules and you got coffee molecules. And then once you start mixing them together, then things get more complex. You don't just see milk and coffee, but you see a mixture of the two. And this would be like equivalent to entropy happening in our universe. So you got milk then coffee, and then you mix the two and the entropy goes up. And as the entropy, the amount of disorder goes up, then the complexity goes up as well. It's not just a simple milk and coffee, but they start blending together and it's more complex. And then as the entropy continues to go up, the complexity continues to go up, and then it goes down, because sooner or later you're just going to have instead of milk and coffee, you're just going to have a mixture of milk and coffee, and it's going to look like this I don't know, silky smooth milk and coffee. And so basically, once you have that mixture of milk and coffee, you can't go back to when they were separated, when it was just milk on top and coffee on the bottom. It's this blend together of milk and coffee now. And that would be equivalent to what the thermal equilibrium looks like when entropy reaches the maximum state and you're at equilibrium. So basically, that is what they did with the experiment of the toy model of the universe, except instead of milk and coffee, they used particles and gravity. And so when you get that combination of milk and coffee, when they are combined into, things are backed to simplicity, which is that it's like complexity starts out simple, then it gets really complex, and then it goes back to simplicity. And so, which is basically saying that simple, and then entropy goes up and it's super complex, and then once you reach the thermal equilibrium, you're back to being really simple. And you can't go back to what it was. So that's how they, because they mixed I can English, I swear. So what they did, like I said, was mix gravity and particles. So with the milk and coffee, when it's mixed together, you can't go back. So with gravity and particles, when they clump together and then separate and go apart, it doesn't go back. So that's why they think, oh, that's the forward motion of time, and that's why we can't go back in the past. Maybe that confused you more. Maybe it didn't. If it did, watch it over again, but we're moving on. So when you apply this whole concept to what happened at the Big Bang, then you see that the complexity gravity theory of the forward motion of time it's still time symmetrical. But it would mean that before the Big Bang, there had to be particles there to clump, because basically that's essentially when the particles clump together, that was like the beginning of the Big Bang. And then when it's spreading apart, that's what we're in now. But at the Big Bang, particles clump together. Yeah. But if you played that backwards, there would have to be a different universe that existed before the Big Bang. It doesn't work unless there was. Now, having said all of that, some physicists like this theory and others do not. And they don't because this theory has not been tested with Einstein's theory of relativity and quantum physics. So if it doesn't work with those, then this entire theory Then this entire theory falls apart. Another interesting fact that has to do with the gravitational complexity theory is that this one physicist, Kozlowski is his last name, says that complexity stores records inside of gravity, which allows gravity to hold information. For example, the rings on a tree. The rings on a tree contain information of the past. What this physicist said is that it works the same with our memories and with our brain, that over time our brains become more complex, and then like the rings on a tree, we have these memories in our brain. So a complex universe contains more records than a less complex universe, which is why it's theorized, which is why we remember the past and not the future. But again, this is only a theory because it has not been tested with Einstein's theory of relativity or quantum mechanics. So having said that, on a particle level, with the standard model particle physics, we still have an issue, and time is still symmetric, and we still don't know the difference between past and future. And the last theory that I've found that could cause the forward motion of time is called causal set theory. And just to really sum this up pretty quickly, that it said that space-time, the plane of space-time, if you will, is made up of small little space-time atoms. And with entropy in the expanding universe, those atoms are constantly being created, and in that motion, forward motion of time, which is why we have that forward motion of time. That's very, very simplified, but that's another theory. Okay, so now that I explained all that, on to the next part. So if everything on a cellular level is time symmetric, that would mean no past, no future. That would mean everything past, present, future is always in the now. The second law of thermodynamics plays a part in our perception of time, but still on a cellular level there is no cause and effect when it comes to time. So there is no forwards and backwards, everything is always in the now. So what does science have to say about now? So for this, we're going to go back a little bit and talk about particle physics. And in talking about the now, we're going to talk about this thing called quantum entanglement.